By referring to the illustrated examples from the previous 5 videos, it is often possible to intuitively identify limits of functions or to identify when limits fail to exist by visually inspecting function plots. We conclude this slide deck with a final video outlining how a limit definition can be used more formally to demonstrate that a particular number is a limit of a function. We want to show that the limit as x approaches 1 of the function whose association rule is 2x equals 2. The association rule 2x corresponds to a straight line. We draw a golden horizontal line at y equals 2 and a blue vertical line at x equals 1. Is it true that we can shade a golden band centered around y equals 2 and find a value of delta that defines blue shaded intervals within which the yellow line remains vertically contained by the golden band? If so, is this true regardless of how thick or how thin we make the golden band? We want to show that for all positive epsilon there exists a positive delta such that confining x to 2 intervals, one of them between 1 minus delta and 1, and the other between 1 and 1 plus delta, ensures that the quantity 2x deviates from the value 2 by a magnitude less than epsilon if it deviates at all. We will accomplish this task in 2 steps. First, we will analyze the range of heights that the function explores when x is restricted to take values within bands of width delta. Then we will use this relationship to specify finite delta so that the function explores heights within a band extending epsilon above and below the putative limiting value of 2. We will be able to obtain a formula for delta that will work for any finite epsilon, completing the proof. Our first step is to ask what range of heights the function explores when x is confined to bands on either side of x equals 1. Consider some arbitrary positive value delta. This vertical yellow arrow is plotted precisely at x equals 1 plus delta. Y max denotes an upper bound on values that f on x can take in the blue shaded bands. No value of f on x in the blue shaded region is bigger than y max. In fact, since the position x equals 1 plus delta corresponds to a dashed vertical line and is thus excluded from the blue shaded region, no value of f on x in the blue shaded region can even match y max in height. Y max equals 2 times the quantity 1 plus delta. This yields 2 plus 2 delta. This shorter vertical yellow arrow is plotted precisely at x equals 1 minus delta. Y min denotes a lower bound on values that f on x can take within the blue shaded bands. No value of f on x in the blue shaded region is as small as y min. Y min equals 2 times the quantity 1 minus delta. This yields 2 minus 2 delta. The values of f on x in the blue shaded bands are between y max and y min. Now that we have identified upper and lower bounds for f on x when x is restricted to take on values within the bands of width delta on the left and right sides of x equals 1, we use this information to tune delta to ensure that within the blue bands, the function is vertically confined to the golden interval between epsilon above and below y equals 2. Pick some arbitrary positive epsilon. How can we adjust delta so as to ensure that within the blue bands the plot of 2x versus x is less than epsilon above or below the value 2? We will satisfy this requirement by insisting that y max and y min both reside within the golden band. We are requiring that the magnitude of the difference between y max and 2 be less than epsilon. In other words, we require that the absolute value of 2 plus 2 delta, that quantity minus 2, be less than epsilon, meaning that we require the absolute value of 2 delta to be less than epsilon. We are also insisting that the magnitude of the difference between y min and 2 be less than epsilon. The absolute value of 2 minus 2 delta, that quantity minus 2, needs to be less than epsilon. In other words, we are requiring that the absolute value of negative 2 delta be less than epsilon. Both conditions on this line correspond to the condition that 2 delta be less than epsilon, in other words, that delta be less than epsilon divided by 2. If we have a positive epsilon and then we also choose some value of delta that is less than half of epsilon, we ensure that the values of the yellow curve for the function 2x within the blue shaded bands are vertically confined to the golden band. Since this confinement is achieved for any finite epsilon big or small, we say that the limit as x approaches 1 of the function whose association rule is 2x equals 2. In this slide deck, we introduced limits by presenting 4 limit definitions. We did this by presenting notation, short vernacular descriptions, symbolic definitions, expanded descriptions in English, and function plots. We also provided examples of how limits can sometimes fail to exist, and in this video, we provided an example outline of how a limit definition could be applied to formally analyze a function. The familiarity with limits that we have developed in this slide deck will help us to investigate derivatives and integrals in upcoming modules. These concepts will be essential for understanding how quantitative scientists specify models for rates of change in physical and biological systems and essential for understanding how quantitative scientists turn models of rates of change into predictions of dynamics.